Deep ominous tone, imagine a temperature so precise that a deviation of just 3 degrees means death. Not for a machine. For an entire civilization. 93 to 95 degrees Fahrenheit. That is the razor-thin margin between life and annihilation for a honeybee colony. In 2026, as the planet shatters heat records, this margin is disappearing. A study from Arizona State University dropped a bombshell. Extreme heat waves are overwhelming the natural defenses of honeybee colonies at a terrifying rate. Smaller colonies experience temperature swings of 11 degrees Celsius at the brood edge. That is not a warning. That is a massacre. When the internal temperature of a hive exceeds 95 degrees, the wax softens. The structure collapses. The larvae cook. Entire colonies can die in hours. 75% of the world's food crops depend on these creatures. If the bees cannot cool their hives, we cannot feed ourselves. But here is the twist: inside every hive, hidden in the geometry of the comb, is a cooling system so advanced that engineers are only beginning to crack its code. The honeycomb is not just a storage unit. It is a mathematical masterpiece. Each cell is a perfect hexagon. Not because bees like 6 sides. Because evolution calculated that the hexagon is the most material-efficient shape in existence. This is the honeycomb conjecture. Mathematician Thomas Hales proved it in 1999. The bees had been using it for over 50 million years. But the shape of a single cell is just the beginning. The honeycomb is a fractal structure. A pattern that repeats at multiple scales, creating an exponential surface area for heat to escape. Think of it as a radiator. The more surface area, the more heat dissipates. A single gram of honeycomb contains over 100 square centimeters of surface area. This fractal geometry turns the entire hive into a passive heat exchanger. Millions of tiny channels venting heat simultaneously. The bees did not build a home. They engineered a thermodynamic machine. But passive geometry alone cannot stop a heat wave. That is where the bees reveal their true genius. When the temperature crosses a critical threshold, a silent command spreads through the hive. Worker bees move to the entrance and begin fanning their wings. Not randomly. In precisely coordinated waves. Thousands of bees. Thousands of wings. Creating a directed airflow that pulls hot air out and draws cool air in. A 2019 study from the Journal of the Royal Society Interface cracked this code. Each bee has a slightly different temperature threshold for fanning. This genetic variation is not an accident. It is a distributed sensor network. Imagine a building where every thermostat is slightly miscalibrated. Together, they create a perfectly smooth temperature regulation curve. That is what bees invented. Then comes the most astonishing feat of all: evaporative cooling. Bees leave the hive, find water, bring it back, and spread it in microscopic films across the comb surface. As the water evaporates, it pulls heat away from the brood nest. The same physics that cools your skin, scaled to an entire civilization. A single hive can move over 1 liter of water per day through this process. This is not instinct. This is calculated thermodynamics executed by a creature with a brain the size of a poppy seed. Now here is why this matters to every human being on this planet. In 2025, buildings consumed over 30% of global energy. The vast majority goes to heating and cooling. Our homes are thermal boxes. They fight the environment instead of working with it. The beehive does not fight heat. It channels it. And after millions of years of evolution, it has perfected the art. Engineers are now studying the honeycomb to redesign how we cool our world. Honeycomb-inspired fin structures and cooling systems have already reduced phase change time by over 10%. That finding came from a 2024 study in the journal Energies. Fractal ventilation corridors, modeled on the airflow pathways of a beehive, can slash cooling costs by up to 30%. In 2026, researchers at the University of Stuttgart unveiled a bio-inspired evaporative cooling facade based on honeybee water management. Their prototype achieved temperature differentials of up to 10 degrees Celsius compared to conventional walls. Imagine a building that breathes like a hive. A wall that sweats like a bee. That is not science fiction. That is biomimicry. And it is happening now. So what shape should our homes take if we want to learn from the bees? The answer is not hexagonal houses. The principle runs deeper. Homes should be designed with fractal-inspired ventilation shafts that use natural convection to move air without a single fan. Walls should incorporate phase-change materials arranged in honeycomb patterns, absorbing heat by day and releasing it at night. Roofs should use hexagonal tessellation to maximize passive radiative cooling into the night sky. Multiple small ventilation openings distributed across a structure regulate temperature more efficiently than one large opening. The distributed sensor strategy of bees' many imperfect sensors working together is already being deployed in smart building management systems. The fractal geometry of the honeycomb is not just beautiful. It is a blueprint for sustainable human architecture. The bees solved the cooling problem millions of years before humans existed. We are only now beginning to read the manual. The world's most important pollinators are dying. Heat is the primary weapon. But inside their hives, written in the sacred geometry of every cell, is the solution that could save them and us. Fractal mathematics. Distributed intelligence. Evaporative precision. Biological engineering perfected over 50 million years. We do not need to invent a new way to cool our planet. We need to pay attention to the teachers that have been here all along. This is Animal Impact.